There we go. Okay, everybody ready? So what? The other class did a good job. Now I know that they are just now doing trigonometry in their math, and so, but I think some of them actually woke up a little bit and said trigonometry is more than just the mechanics. You know, the teacher says, "Here's how you do the problem." I know how to do the problem, but we actually explored it a little bit and said, "What if you do it this way? What if you do it this way?" And I think they understood a little bit more about trigonometry. So, now again, I'm not trying to put you down. Matter of fact, you guys are up, not down. But be careful about the fact, let's say you're really good at trigonometry, the mechanics. Are you good at applying it to a situation? All right, so let's take a look. And I probably would not give you a question like number 1, but here's what I'd be looking for in the quiz. If there were 5 points apiece, I would be looking for a diagram, and the math would be worth 3 points, and the answer would be worth 2 points. You get that? So I want you to learn how to draw diagrams, and I want you to be able to label them. So if we look over here, this is flip, and this is a simple diagram, and I wouldn't have this on a quiz, too simple. But I would be looking for some kind of a vector here, and how would you label that vector right here? What would that be called?
Gravity.
It could be, and I know the book likes to say the word gravity, but what actually is it called?
Weight.
It's weight. And so weight is a force, isn't it? Isn't weight a force? And so what we have is, that would be the weight vector, and then your diagram, because he's in equilibrium, I would draw another arrow here, which knows, I know that he's in equilibrium because there must be an upward force of 650 newtons. But he's not being lifted up by 1 wire, he's being lifted up by 2. So then I would see not this size of arrow, but a smaller size. Isn't it about half? So it should be about half the size of that arrow, and it says 325 newtons. But how would you label this one? How would you label that vector? Is there a name for this? And, you know, physics people are, just like math people, are notorious for using subscripts that are numbers. Remember that? Remember the first time you saw that? What in the world is that? What are those little tiny numbers meant? And subscripts are name tags. This is not squared. This is the second X number. That's who you are. And so if math people are notorious for using number subscripts, physics people are notorious for using letter subscripts. Some people look at something in physics and they say, oh, who can understand that? Really, most of it is just letters with subscript letters. You get it? And what force would this be? This could be called the force called weight. And what would you label this guy here? What is this called? Tension. And so maybe you'd see a book to say F sub T, the tension force. Ever get that? Okay, so that's the one thing I think people get hung up on in physics the most are the little labels they have on there. Okay, let's go to the next one now. The next one was a picture that was hanging, and even in this case, the picture weighed 126 newtons. We know that this wire, there's a tension force going this way on that wire and the one going this way. So in a way, this wire is not asking to support the whole weight. And if we split it up into a triangle like this, what would you call this? What would be the magnitude of this vector here? What would be the magnitude of this vector? And matter of fact, there'd be 2 of these triangles, wouldn't there? Wouldn't there be one of these and then right next to another one? And what would be the magnitude of this one? Help me out. How much? Blah, 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 blah. What do you think? Rollins, what you got? What would be the magnitude? This is the problem we did yesterday. What's the magnitude of this vector? If I had to draw the triangle representing my work, what would the magnitude of this vector be? Would it be 126? 63. So it's only half, right? Everybody see that? And so this would be labeled as 63 newtons up here. And this is your tension force. What you're really trying to find is the tension force, isn't it? Okay, so now, this one actually had 3 ways of doing this problem. The good news was, because that was a 90-degree angle and I split it in half, then that's 45, and that's 90. So one way we could just do it is 63 times the square root of 2. That's method number 1. Now let's try another method. I want to see this triangle through the eyes of this 45-degree angle. And so seen through the eyes of this 45-degree angle, I am called the opposite, and I want to find the hypotenuse. So which trig function do I use if I have the opposite and hypotenuse?
Sine.
And there you go. And so we say the sine, as seen through the eyes of a 45-degree angle, should be the ratio of this over that. You do a little math here, and you get 89.1 newtons. Remember doing that yesterday? Now, what if the author actually saw the triangle through the eyes of this 45-degree angle? So what happened here? When you see it through the eyes of this 45-degree angle, then that 63 is what? As seen through the eyes of this angle, who is the 63? He's not opposite. He's adjacent, isn't he? Now, adjacent, and I want to find hypotenuse, so the author said, I'm going to see the triangle seen through the eyes of this angle, and now use cosine. I don't know if some of you have already figured this out, that the sine of 45 and the cosine of 45 are what? They're equal, aren't they? And so you could do this problem with sine or cosine, and you'll get the same answer, won't you? All right, let's do the next one. This is the one I think we got a little interrupted on, and let's see how far we got here. Michelle likes to swing on a tire swing, and okay, so if we were going to make a diagram here, here's our triangle here, but we actually only have there's only one rope here, isn't there? And what are we trying to find? We're trying to find the tension force. Everybody get it? Okay, so now, here's what we know. We know they pulled it back, and the angle here is 30 degrees. We know that. Do we know this? Do we know how much force is going this way? We don't know that one, do we? We want to find this one, and I have the angle, but I'm in trouble because I need something else. So what else do we know? I'm keep looking. All right. What else do we know? All right. Raise your hand if you know. You just don't want to say it. How about that? Okay. All right. Why don't you? What do you think? What is it?
Well, it says the combined weight of Michelle and the tire swing is 825 newtons.
Say it again.
The combined weight of Michelle and the tire.
All right. So we know that that vector right there is actually 825 newtons in magnitude. Is that right? So that's good because now I have this side, and I have the angle, and I want to find the hypotenuse, right? So let's try it one way. One way. As seen through the eyes of the 30-degree angle, who am I? As seen through the eyes of the 30-degree angle, who am I? Everybody. Adjacent. And I want to find hypotenuse, so that's why you could use cosine. So the cosine of 30 degrees equals 825 over the tension force. Do a little math here, and you come up with about 953 newtons. But what if we wanted to do it differently? Could we see the triangle through the eyes of this angle? So then what would we do? As seen through the eyes of this angle, who are you? That's opposite, isn't it? If that's opposite, and I want to find hypotenuse, then I could do sine, not of 30, but what? The sine of 60 degrees would equal 825 over the hypotenuse there. And what would happen if I solve for that? And I know you guys, like I said, you're more advanced in math, and most of you, maybe not everybody, maybe you do know that the cosine of 30 degrees is the same as what? The sine of 60 degrees, isn't it? And we're going to get the same answer, aren't we? So it's kind of nice if you could do it more than one way. I think you'll actually feel a little bit better about trigonometry and how to use it like that. All right, so what I'm going to do, I'm not sure why you're so quiet today. What I'd like to do is, on the next problem, I'd like you to do it by yourself, okay? So let's get a piece of paper out, draw the diagram, and see if you can figure this one out on your own, and say, I have a nice diagram, it's all labeled, and I'm not going to look at the answer. I don't want to look at the answer until I've done it. So when I get finished, then I'll check my answer with the author. All right, let's go ahead and do that. Draw your diagram, try to label it. said one each row? Okay, I thought you meant, was that, what's your label, was that G? Oh, sorry, that's not it. But, it is true that, if you make a triangle, only half of this 2 newtons is supported by this wire, so I thought that's what you meant by that. 1 newton. Try it again. The only thing about this problem, which makes it different, is that we never do know the angle. So even though a lot of people, they do remember trig, so we give the angles and I'll look it up, tangent of 30 degrees, tangent of 45. But what if I give you the tangent? What if I give you the tangent and you go opposite and actually find the angle that would produce that ratio? And again, each math teacher has their own vocabulary. Does your math teacher use the word like cosine minus 1? Do they say inverse sine? What words do they use? Oh, cotangent? They don't say inverse sine. They don't use that word terminology. Okay, all right. So a lot of times in physics books, you're more likely to find sine minus 1, sine to the minus 1 power, which is like inverse sine, which would be your math teacher called cosine. I mean, your math teacher called what's sine minus 1? What's inverse sine for your math teacher?
Cosecant.
Cosecant. Okay. What's he called inverse tangent? Cotangent. Okay. All right. So how are we doing? This one a little bit harder? Now, if you don't get the same answer as the author, one mistake, which I've been trying to, I try to do that all year, but units are real important. So I noticed that one of these units talked about meters, like the clothesline was 6 meters long, but how far did it bend down? It didn't bend down 4 meters, it only bent down 4 centimeters. So you're not going to be able to do a problem where some of your units are meters and some are centimeters, so you're going to change everything to meters. So if you didn't change everything to meters, that might be one of the problems you're having. Yeah, Owen.
Actually,
I'm sorry, okay. All right, let's everybody look up here now. So let's see, is there only one way to do this problem? Oh, let's see, maybe let's take a look. So here's and by the way, if I had to draw this model to scale, here's what it would look like. Here's 6 meters. It only dips 4 centimeters compared to 6 meters. So the real one will look like this. So the real diagram would look like that. The wire would only bend a little bit, wouldn't it? And so that's hard to, the reason they exaggerated it so you could actually see the triangle. So the real one, it only bends a little bit. So this is 3 meters, that's half of 6, and this is 0.04 meters. So I had to change the centimeters to meters. So let's take a look, all right? Everybody look up here for a minute. I want to find this tension force, don't I? So what do I know? Well, I don't know. This is the right triangle, and one of these would be called the opposite, one would be called the adjacent. So why don't we take this angle right here, okay? All right, here we go. As seen through the eyes of this angle theta, as seen through that angle, who am I? Opposite, and who am I? Adjacent. Well, which trig function uses opposite and adjacent? Everybody. Tangent. The tangent as seen through the eyes of this angle would be 0.04 over 3 meters. All right, so anyway, what you do is get a number here, and then that number is the tangent, by the way. That decimal you get there, that is the tangent. But I don't want the tangent, I want the angle. So then what do you have to do? What can everybody tell me what you got here? Hey, did you do this one yet? 0.0133, okay. And for whatever answer, for a reason, the author stopped at 0.013. I'm going to go ahead and use 0.0133, okay? Let's do that. Now, the tangent of some angle, there's some kind of angle that would have produced this ratio of 0.0133. That is the tangent, but I don't want the angle. So how do we have to do that? We have to do, you said you call it cotangent in your class? Okay, the physics books would probably say tangent minus 1 or inverse tangent. What is the inverse tangent of 0.0133? All right, somebody else. Clayton, do you have that one? What's the inverse tangent of that? Did you do it this way? Is this how you do the problem? You do it differently?
Yeah.
Okay. All right, what is it?
But it's, I got
0.74? Now, did you use 0.0133 or did you use 0.113? Okay, let's use 0.0133 because I think we get a better answer than that. What'd you get?
0.7620.
Okay, everybody got that? All right, so anyway, the angle, by the way, that's not a tangent anymore. That's the angle, isn't it? It's a tiny angle. It's less than 1 degree angle. So I do know theta, this angle here is that. So now, here we go. As seen through the eyes of 0.762 degree angle, all right, the tangent, not tangent, I'm sorry. As seen through this angle, I can go this one and this one. So I could use opposite and hypotenuse. I could do sine, or I could go adjacent and hypotenuse, cosine. Which one do you like? Here's what I'd like you to do, all right? I'd like you to try them both. So let's try it. The sine of this angle, as seen through the eyes of that angle, equals the opposite, which is 0.04. Make sure I do meters. Oh, wait a minute. I'm sorry. Oops. Is that right? Okay. Is that how you did it? How many of you use sine? How many of you use sine on this one? Okay, so when you solve for FT, what did you get?
for FT,
10. 75. Huh. That didn't seem right.
It's because I did the same thing on, it's because they only rounded to 0.013.
Okay. Oh, I see. I'm sorry. So you got 75 newtons?
I got 75.38, basically 75.
Okay. All right, so about 75 newtons, is that right? Okay. Okay. What about, did anybody use cosine? What did you get?
I got 75 minutes.
Okay. All right, so what do you think? Let's look at that again. What do you have? What is the sign? Can you look at what is the sign of 0.176 or 0.762 degrees? What is that?
Yeah,
0.01. Say it again.
333.
Okay. All right. So you're saying that's the sign, and that equals 0.04 over ft. What if we did that? What happens then? Now, here's something to think about. I used distances to find this angle, but what about this? What's going to happen here if you use this number here? What if I use that number there? What will that give me? That would give me in meters, right? So if you put this in there, you don't get 75 if you use this, do you? Everybody, would you use 75? Try that and see if you get 75. What's 0.04 divided by that? Is that 75? What's 0.04 divided by 0.0133? Somebody give me a hit on the calculator. Ian, what do you got? What's 0.04 divided by 0.0133?
3.008.
All right, now, so which one is right? And what's wrong? I made a mistake here, but what's wrong with this? I put 0.04 here. We had to use the distances to find the angle, but what's wrong with that? What should I put here? What is it? Right. Matter of fact, in newtons, if the whole swimming suit weighed 2 newtons, only 1 newton is represented by that vector, isn't it? No, I'm sorry, this one right here. Okay, so let's put a 1 here and see what happens. All right, now what do you get? What's 1? Do you have a calculator, Maggie? What's 1 divided by 0.0133? Okay, so the tricky part of this one was we used distance units to figure out the angle, but then we had to switch into the vector world. I was trying to find this vector, and so I can't use 0.04 here because that's a distance unit, so we had to use half the weight, so we used 1 Newton here. Okay, sorry, I shouldn't have written that down. All right, what do you think? Now, I'll tell you what's strange about that is the whole swimming suit only weighs how much? Isn't it? It's kind of strange. I mean, I didn't make up this example, but this one still seems kind of strange to me. It's only a 2 Newton bathing suit, and they're saying how much tension is in that wire. I don't know about that. Something doesn't seem right, does it? What are they saying? 77 newtons of tension is in that wire? I mean, either that wire, I don't know. That seems strange to me, doesn't it? Does that seem strange to you? No? No comment? Okay. All right, yes.
I'd say it doesn't seem strange because if you pull down a rope, it like slingshots back up.
I agree. If I were to hang on that rope, I could see a really large tension going on there, but a 2 Newton bathing suit is pretty small. The only thing I can think of is it must have been sort of tight. It must have been a pretty tight rope. And then they put a 2 Newton on there, and it produced a huge 79 Newton force going this way. And by the way, the real diagram looks like this. Watch. And that's what you did on the worksheet yesterday. 79 newtons this way, or 77 newtons this way, and 77 newtons this way equals 2 newtons up this way. See that? And that's weird. So it is huge. All right, questions on that? All right, so what I did is tomorrow I think there are like 5 problems like this. And what I'd like to do is kind of get used to drawing the diagram and label it and then showing your work, all right? All right, I'm gonna stop that for a minute and we're gonna switch gears a little bit. All right. So tomorrow we'll wrap up we'll take a quiz like the first 15 minutes or something like that. And then we'll get back into this. Chapter 3, I'm not gonna spend a huge amount of time on because you actually know a certain amount of this already. But I do want to talk about and I'm really glad to hear that the humanities teachers are still doing a little bit of science in there. And I heard that you guys have already talked about Aristotle. Is that correct? And had you talked about any of his the Aristotelian views? Did they use that word, Aristotelian? Okay. Anyway, so they had a little brief article about Aristotle. And Aristotle, why does everybody know his name? Well, okay, he was a thinker. He was a philosopher. And what he did is he seemed to comment on like lots of things. I read another article. It said he talked about pain. He talked about animals. He talked about physics. He seemed to have something to say about everything. Now, he based most of his stuff on what people saw. And so, believe it or not, he said, well, if they're in the ocean, they're going to call them fish. And so if we're going to name them, we need to name them with the word fish. And today, we still call that blob of jelly, we call it a jellyfish, even though there's no way it's a fish. We have, so he liked to call things in the ocean fish. And so they thought that was smart, and people probably thought, that makes sense to me. And then we found out later there's actually mammals in the ocean, right? There were things like whales and porpoises, and they're not fish. Oh, okay, we made a mistake there. But anyway, Aristotle did have a lot to say about things, and I know what you might be thinking, and this is called a little bit of pride or arrogance, and you know what? I know exactly what you're feeling, because I'm sure I was just sort of like you. Some of you have a certain amount of pride or arrogance in that you're probably thinking, well, I wouldn't think like that because I'm so much smarter. We're so much smarter than people way back in the times of Aristotle. But I can tell you that almost every one of you in this class, you think Aristotelian. Your thoughts are very, very similar to what Aristotle would have said was true. And Aristotle, what he said was true long after he died, like 1,500 years. It was true everywhere in the world where you had any kind of education, even in the church. His things were so true that nobody questioned them. And that was a big problem. So Aristotle would have had, and here's where your humanities teacher came in a little bit. Aristotle would have said, well, we live on a planet that's sitting still because I don't feel myself moving. And everybody says, yeah, that's right. And the sun goes around the earth because I see it going around the earth. And at night, I can see the moon going around the earth, and the stars move around the earth. And that was called a geocentric theory because geo means earth. And the whole idea, and it made a whole lot of sense. There's no way the church didn't buy into that, and they believed very strongly about the geocentric theory. They even thought, well, no wonder God made humans special, so no wonder we're the center of the universe. And yet nothing in the Bible says that we're the center of the universe. But it was seen as true. Well, then he has some other ideas, okay? Here's one. Here's an object. See the object? He says, let me tell you about moving objects. And here's the Aristotelian view. And watch. This is the way you think, honestly. If you want an object to move, you got to put a force on it. If you stop that force, it's going to stop moving. As a matter of fact, even if I put a force in there, he said all moving objects have a tendency, first of all, you have to put a force on them to make them move. And if they're moving, they all have a tendency to slow down and come to rest. Yeah, that's what I've seen my whole life. I threw a baseball at it. You know what I did? It slowed down and came to rest. Yeah, this is true. You're going to find out later that Galileo is trying to fight that. He's going to try to show you that didn't make any sense at all. What do you mean it doesn't make any sense? That's what I see. So the Aristotelian view says, if you want something to move, you better put a force on it. You want it to keep moving, you better keep putting a force on it. When they had, like for example, an arrow. You shoot an arrow, or you shoot a cannonball. You know what people thought? People thought, because of the Aristotelian view, that as the cannonball went through the air, some of the air got behind the cannonball and kept going like this. Whoop, 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 whoop. And they thought, why would a cannonball keep moving? And they would have said, something behind the cannonball keeps pushing it. And that, well, kind of makes sense to me. All right, some other things that Aristotle would have said. He would have said that light objects can't fall as fast as a heavy object. And I know I might have done this earlier in the year. I'll do it again just so to make a point again. I don't think Galileo ever did this experiment, but it would have been neat to go back then and do it. So you say Aristotle says light objects cannot fall as fast as a heavy object. So if I drop both of these, which one's going to hit the ground first? See that? He said, all right, ready? Which one? If I drop both these, then which one hits the ground first?
Cool. But what time do
Okay,
you
watch now, watch. No, you're wrong. Okay, now, if I say, well, come on, man. You tricked me. All right, what if I drop them at the same time? Which one falls faster rate? How about that? What do you think? Good look, okay? See, look. Oh, you're wrong again. Okay, now you say, oh, wait a minute. What if you drop them at the same time and you don't put the paper underneath it? Okay, now which one hits? You're wrong again. Now, so, and then you said, okay, what if you drop them at the same time, but you don't let this come in contact with the book? How about that? Now which one hits the ground first? And I know what you're thinking, oh, you. I didn't add any mass to this, did I? You were wrong again. And so when Aristotle says that light objects cannot fall as fast as a heavy object, that was true for 1,500 years. But imagine, here's Galileo, and here's what he was good at. Galileo loved arguing. And if people criticize, oh, you're wrong, he'd use your own logic against you. Now, he wasn't in the same time period. Aristotle was like 300 BC, and Galileo was like 1600, okay? But if they met, he might have said something like this. Aristotle, let's go to the top of a tall building. Let's take an anvil. Does everybody know what an anvil is? Like in cartoons, anvil. It's heavy. It's a heavy piece of steel. Let's take an anvil, and let's take a hammer, and the hammer's not as heavy as it. Galileo, Aristotle, what if we drop these from the same building? You're saying that the anvil will hit the ground first because it will fall faster than the hammer. Is that correct? He said, yes. Well, they never really did that, but it's possible the anvil might win, maybe, or they hit at the same time. But here's what Galileo said. Aristotle, let's have an anvil by itself and an anvil with a hammer tied onto it. Let's drop both of those at the same time. Your logic says the anvil and the hammer have a bigger mass, so they have to hit the ground first. And your logic says the anvil and the hammer can't fall as fast because the hammer will prevent them from falling as fast, like a parachute. And then the anvil by itself will hit first. And so what he did is, logically, it wouldn't make any sense. It wouldn't make any sense to say heavy objects fall faster than light objects. But why was it true for 1,500 years? Because that's what people saw. When you see a stick fall, it falls at this rate. You see a leaf fall, it's really slow, isn't it? And yeah, we're just getting fooled. We get fooled because of air resistance, don't we? So that's what he would have done. Galileo would have used logic like this. I'll show you a couple more he did. Oh, I need my broken book. I'll show you a different book. And I think if you do any kind of research on Galileo, I think you'll find that he was a genius. I have no doubt that I can't even believe that he came up with some of the ideas he did. Here's one of my favorite things. Here's Galileo says, let's talk about the Aristotelian view about objects have a tendency to come to rest, okay? Let's try that. What happens if I put a ball on a ramp and it goes down? What happens to the speed of the ball? You say, well, it speeds up. And everybody agrees that's what happens. What happens if a moving object goes uphill? You say, well, it always slows down. That's always happened. Okay. What about a moving object that's not going uphill or downhill? It can't speed up and it can't slow down. So what's it going to do? It's going to keep moving at the same speed. There's no tendency to slow down. There's no tendency to speed up. If you're in a straight line and you're moving, you have a tendency to keep going at that speed. Now these, he actually had real ramps made. He had ramps made, and they're actually in a museum in Italy. And so you had half a ramp here and half a ramp here. And so what happened is, he would roll this ball down, and he'd say, when do you think it's going to stop rolling? And somebody said, well, it's going to stop here because it went down this far, it'll go up that far. Then he replaced this ramp with a ramp that was not as steep. And he said, well, how far do you think it's going to roll? Well, they said, it rolled down this far, it'll roll up this far. But even though there was friction, it never stopped there. It kept rolling and kept rolling until it reached what? See that? The original height. Until it reached about the original height. And then he said, let's replace this ramp with this one. Now tell me when the ball is going to stop. It doesn't stop until it reaches the original height, right? So what's it going to do? What has a tendency to do? To keep moving at a constant speed in a straight line forever. Forever. Now imagine somebody who didn't know really what space was, or he didn't know what it would be like to be in an environment with no friction. They didn't know that, but he's able to figure it out. So that's when the Galilean ideas kind of started to take over. And again, about 1600s, even Galileo got in trouble. Galileo, if you want to read about him, I'd like you to read about him, but one thing he did like to do is he liked to write these things called dialogues. And you can look these up, but a dialogue would be, and he made some names, like one name might be called Simplico versus this other name. And Simplico would be the person who might think like Aristotle, the Aristotelian view. And so Simplico would say, well, no, this is why it happened. And then the person who knows what they're talking about would say, no. And they try to use their logic against them and say, that's not even logical. Now, Galileo liked the church. He was not enemies of the church, but it just so happened that he did have a feud. There was something that went on with the church. Have you read that? And have you had that in humanities class yet?
Yes.
Okay, and I don't know how your humanities teacher slanted it or didn't slant it. I don't know. But he was not an enemy of the church, but when the church saw some of Galileo's ideas, and they said, you know what? When we kind of fused the Aristotelian view with biblical stuff, and that whole thing became true, when you start talking about stuff that we thought was true, it's not biblical, but we thought, you're telling us not true, that's like blasphemy. You're saying, well, now nothing's true. Now you're attacking the whole church. And so he got in trouble because he had some views that said the thing that the church said was true is probably not true. And that was not good. So the church asked him to recant that. And so he got in a little trouble with that. And now he did get, because the church was powerful enough at the time, they didn't put him in jail, but they did put him in house arrest. And at that point, then he couldn't really do exactly everything he wanted to. The good news, some of his work did come out, and a lot of it was preserved, and that's how we hear about Galileo today. I have a book back there if somebody would like to read it. It talked about feuds. Can you see that book? Is that book back there? If you there's another one too. There's another one talking about feuds. It might be a hardback book. Okay. But anyway, so a lot of people, I will tell you this. If you were an atheist, you would say that science and church just don't get along. And they would like you to believe that because, yeah, that's it. Great feuds in science, that's it. But they would like you to believe that, but that is not true. That if you look throughout history, there was no real conflict between the church and science. This was a conflict because he thought they were attacking true things that were not really biblical. That was the church's fault for thinking that was a blasphemy when it was not biblical at all. One thing that Galileo got in trouble, another thing he got in trouble with, is one of his dialogues that he wrote. It was kind of like the way the Pope thought. And so the Pope thought, when this guy named Simplico, who was not he didn't come across very smart in the book, people said to the Pope, "That's you, Pope, he's trying to talk about you." And we can't have the people thinking that the Pope is some dumb person. And that's really where he got in the most trouble, is when they accused him of writing about the Pope. But anyway, and Galileo, even though you could say he recanted it, there's no way that the rest of his life, everything else he wrote, he didn't recant. He knew that was true. So anyway, I don't know how much, have you guys done any kind of reading about Galileo in your humanities? Oh, you have? That's great. That's great. Which class is that?
Bible.
What's it called?
Bible.
Oh, Bible. Wow. And who's your Bible teacher?
Telfer.
Okay, so he's talking about Galileo. That's great.
Did you know that he wrote a book?
He wrote a book?
Yeah.
Yes.
I didn't know that.
Second Thessalonians.
2 Thessalonians?
Yeah.
So it's
That-
called receiving second.
Oh, that's what I said, 2 Thessalonians. But, all right, what we're going to do, what we're going to do is just leave your stuff here, and we're going to go out and line, okay? I thought you were going to say 3rd Thessalonians or something like that. I said, all right, I missed that one.